Okay, good morning. Today we will cover Zener diodes and Zener regulators. That's the usual number. There's quite a few Zoom. So, all right, let's see here. Okay, so we introduce a little bit of the Zener diode last class, and we looked at the reverse bias characteristic. Okay, few key things to keep in mind is when we analyze Zener diodes, the positive reference, of course, for the diode itself is still at the anode. So if you refer to the diode voltage, we would say VD is minus or ID would be minus. But for Zener diodes, it's opposite because Zener diodes are always exclusively used in the reverse bias region. And so when we refer to Zener voltage and Zener current, it is the opposite of what we take for the diode voltage and diode current. So diode voltage, as shown here, has a positive reference at the anode, but the Zener voltage is taken as positive at the cathode and negative at the anode. And so that's the key thing to keep in mind. And the same thing for the current. The actual diode current, of course, is always taken from anode to the cathode, which is ID, shown right here. But Zener current always follows this path. Again, because Zener diodes are used in reverse bias, so the current is flowing in the opposite direction. And so IZ would be positive. And the reason for this, of course, is again, we use Zeners exclusively in the reverse breakdown region, and the voltage is taken parallel across the Zener diode with a positive reference at the cathode. Okay. And this is the region of interest right here. Okay. In the reverse breakdown region, we can see that the voltage is at a very constant level. VZ is held near constant for an significant increase in current. Okay, so the current increases, but the voltage remains constant. The reason for that, of course, is that the heavy doping results in a heavy influx of carriers in the opposite direction. Okay. All right, so those are the properties. Basically, voltage is held constant, VZ is held near constant with an increase in IZ. So the way it is used is, of course, it's connected in parallel to the load, or to be more accurate, the load is connected in parallel to the Zener diode. When they are both in parallel, the Zener current can increase while the load current and the load voltage remain the same. So we will look at load regulation circuit. There are three examples. The first one is where we analyze a Zener diode using the load line analysis. The second example is where we use the piecewise linear model. And the third is where we will apply the Zener diode to perform load regulation. Okay. So this here is an example of analyzing a Zener diode using the load line method. And as with the regular silicon diodes or regular diodes, load line analysis requires that we write a equation for the circuit containing the Zener voltage and the Zener current. So the typical characteristic for a Zener diode is given here. The reverse breakdown effect is a little bit exaggerated to display a slope. Typically, it'd be a very straight line, but right now it's showing a slope right here. Okay. Now, when we write the load line equations and we plot it, this is what you're going to obtain. And of course, the intersection of the load line and the diode characteristic gives us the Q point or the operating point for this particular Zener diode. Okay. And again, Q point would be find VZQ and IZQ. Okay. So let's write KVL around the circuit. And from KVL, we can write minus 20 is equal to VD plus the voltage drop across the 5000K resistor. So it is 5000 times ID. Okay. Remember that first analysis we performed, it's exactly the same. Simply write a KVL around the loop, and you'd have two unknown variables in there, VD and ID, the diode voltage and the diode current. Then we simply choose values for VD and ID as equal to 0 and calculate the other end. Okay. So if VD is equal to 0, then ID, straightforward, minus 20 over 5000 gives us minus 4 milliamps. Okay. And we see that it still falls within our range right there. Minus 4 milliamps. Okay, so we obtain a value for ID on the y-axis. So far, so good. Okay. All right, so next we want to find the other end or the other point, which would be somewhere around here, very far off. And so instead of doing that, we'll make an educated guess. We want it to intersect the characteristic at some point, right? So we will choose, for the other point, we will choose the voltage as VZ at 5 volts. Okay, so instead of ID, we will now choose VD as 5 volts, and we calculate ID for that particular value. Okay, so VD is 5 volts, actually minus 5 volts to be more, right? Minus 5 volts. Then ID is simply minus 3 milliamps. Okay, minus 3 milliamps. Does that make sense? Right, we want it to intersect the curve, and so the best possible choice is to simply use the Zener diode voltage. The Zener diode voltage is 5 volts, so we choose VD as 5 volts to obtain the other intersection point. Okay, so now we have 2 points. That's minus 4, and that one is minus 3. Draw the load line. It intersects right here. And from the graph, again, remember eyeballing the values. So it gets a little difficult, but it's, let's see, we extend this. So it's slightly less than 5.5, maybe 1, 2, 3, perhaps. In the book example, they take it as VZQ as minus 5.2 volts. Minus 5.2 volts. Okay. And IZQ is slightly smaller than 3. I would say estimate around here or even less than that. Okay, so maybe around 2.9 or so. So IZQ would be minus 2.9. Okay, minus 2.9. That is the load line analysis, determining the Q points of the Zener diode using the load line analysis. All right, questions? Yes. Oh, that would be from the manufacturer. Like the question is asked about the diode characteristic, right? Yeah. Yeah, it's provided from the manufacturer. Yep. It still works. Yeah. And again, this is kind of, if you see, the forward bias actually has more of a slope rather than reverse bias. But in here, just to use an example, the authors are using the forward bias does not have a slope at all, whereas the reverse breakdown does have a slope. Just to make a point saying that even if it's a 5-volt Zener, depending on the characteristic, that 5-volt could move to 5.1, 5.2, depending on the slope. But again, as I said, even real life Zener diodes, the slope is very steep. It's almost nearly a flat vertical line in the reverse bias. I'm talking about this one. Okay. Any questions? All good. Okay. So then let's analyze a circuit using the piecewise linear model. In the piecewise linear model, we portray the Zener diode as a voltage source because it is supplying a constant voltage source, and because it will have some resistance to overcome, we model it as RZ. And so in a piecewise linear model, the model requires two things: Zener voltage and Zener resistance RZ. Okay, Zener voltage and Zener resistance RZ. Now, in this case, if you notice, we are not working with diodes VD and ID, diode voltage or diode current anymore. Simply referring to VZ and IZ, and we'll work off that. All right. Okay. So in the piecewise linear model, first make an assumption. Assumption, of course, is whether the diode is on or not, meaning whether it's working in the reverse region or not. Okay. In this case, if we assume that diode is on, logically, it would make sense because our input voltage is larger than the Zener voltage. If the input voltage was smaller than the Zener voltage, then it would not turn on. Okay. For a Zener diode to turn on, the supply voltage coming into the Zener must be larger than the Zener voltage. Okay. And in this case, we see Vs, the supply voltage, is 20 volts, which is larger than Vz. So it's a safe bet to assume that the Zener is going to be on. So we assume that D is on, meaning it is going to supply 5 volts right here. Vz is 5 volts. And Rz is 100 ohms. Okay, 100 ohms. So again, same procedure as we learned earlier. We apply KVL. And once you apply KVL, we sum up the voltages around the loop. We have 20 minus 5,000 plus 100, so 5,100 IZ minus 5 is equal to 0. Right? 20 volts being supplied, everything else being consumed inside. And so 20 minus 5,100 IZ minus 5 is equal to 0. And we solve for IZ, and IZ comes to be 20 minus 5 divided by 5,100. 2.94 milliamps. Okay. Simply apply KVL around the loop. We first make an assumption, then we apply KVL around the loop. Write our equation, solve for the Zener current. So solve for IZ. The key thing here is, since the Zener diode is on, then current should be flowing through the Zener from the cathode to the anode. Okay. And if IZ is greater than 0, then diode is on. Okay. As I said, ignore the ID. We work with ID, we simply work with VZ and IZ. So if Zener is on, IZ must be flowing. It will have a positive number. Okay, it will have a number. So IZ must be greater than or equal to 0. And in this case, IZ is greater than 0. Hence, our assumption is valid. Assumption is valid. Okay. All right, let's take a pause. Let me know if you have any questions. Any questions from anyone? No. So far, so good. Okay. Then let's apply the Zener diode for its main purpose, which is using it as a voltage regulator. Okay. Voltage regulation simply means you're regulating the incoming voltage and providing a constant voltage at the output. Okay. As if you recall, I stated, once you have our rectifier circuits, we convert AC to DC, and we apply a filter capacitor. The filter capacitor will still have some ripples. But if you connect a Zener at the output of that capacitor, the Zener will regulate the input voltage and provide a near constant output voltage. A flat line, constant voltage, meaning a pure DC level. Okay. All right, so let's take a look. What do we have here? We have a Zener diode. We are given the Zener diode voltage at VZ as 5 volts. Zener resistance is 0. We have current IS coming from the source. We have current IZ coming down here. We have IL flowing through the resistor RL. And we'll describe voltage across that load resistor RL as VL. Okay. Load regulation means, or voltage regulation means, keeping VL constant. Okay, keeping VL constant, which is of course what we want in our devices, right? So load should be seeing or should be able to see a constant voltage. And VL thus should be equal to VC. Okay. How much is a source voltage? 20 volts, right? It's higher than the Zener voltage. So our assumption would be that the Zener diode is on and it's conducting and it's providing output voltage at 5 volts. So since Vs is greater than Vz, assume diode is on, D is on. Let's refer to this as Vs, source voltage Vs. Okay. Right. So let's apply KCL at the top. And we obtain IS, source total source current, is equal to IZ plus IL. IZ plus IL. Rearrange the terms. We get IZ is IS minus IL. Right, nodal analysis. Express each current in terms of the node voltages. And so we can write IZ is equal to source current. Source current is passing through the 5,000 ohm resistor, which is connected between Vs and VL. So I can write Vs minus VL divided by R, and here it would be VL over RL. Right? Our assumption is diode is on. If the diode is on, then IZ must have a positive value. And so we write KCL at the top. And we obtain IZ is equal to source current minus the load current. And this is the key equation in all voltage regulators. Okay. You have a total current coming from the source that will be divided between the load and the Zener diode. Okay. If the voltage from the source increases, right now, of course, it's constant DC voltage, but let's say it's varying between 10 and 20 volts. If the voltage increases, then there's extra current coming from, or the current IS coming from the source also increases. But we want to keep the output voltage and the load current, meaning the load voltage and load current, as constant. So the Zener diode, the extra current, flows through the Zener diode in parallel. And because it is working in the reverse breakdown voltage, reverse breakdown region, the increase in current does not affect the Zener voltage. And that is how all these voltage regulators work. Okay. The Zener absorbs the extra current that's coming from the source and maintains the output voltage constant. So here we plug in the values and we obtain IZ as 20 minus 5 divided by 5,000 minus 5,000. This gives us a value of IZ as 2 milliamps. A positive number, a positive value. Hence IZ is greater than 0. Solution is valid. All right, let's take a pause, write it down. Let me know if you have any questions. No questions. Everything makes sense. We ready for a pop quiz? Right now, yeah. I like the confidence. So far, so good. Anyone? Okay. So as I was saying, the key thing to keep in mind is voltage output. So output voltage is always taken in parallel across the Zener diode. And if there's increase in voltage, which means there's increase in source current, the Zener allows a pathway for the extra current to flow through, thus keeping the output voltage and the output current constant. But what if there is a change in the load resistance? If there's a change in the load resistance, does the output stay the same? The answer is not really, no. The circuit would change, right? The current flowing through the output resistance would change. And so there is a minimum value of the load resistor that would be suited to a particular circuit, okay? There's also a max value. So there is usually sometimes minimum and maximum values of the load resistor. So in order for the Zener to work effectively as a voltage regulator, the load resistor must have a minimum value. So in this case, we can derive that minimum value by setting actually from the previous equation itself, right? So for proper regulation, the Zener must be on. For the Zener to be on, Iz must be positive, meaning Iz must be greater than or equal to 0. If the voltage is less than the Zener voltage, the diode will not turn on. It'll simply be VL is equal to Vin, right? So for proper regulation, Iz must always be greater than 0. Because if the load resistor falls below a minimum value, then the load current is going to increase and the Zener will not receive, sufficient levels to turn on. So if Iz must be on, we can take the previous equation and we can state Vs minus VL over R and minus VL over RL must be greater than or equal to 0. Therefore, Vs minus VL over R must be greater than or equal to 0 for VL or RL. And we rearrange the terms and we can obtain RL must be greater than or equal to 0. Oh, sorry, RL must be greater than or equal to VZ over VS minus VZ times R. So that is the minimum value. RL minimum. Okay. RL minimum. That R is also sometimes known as the series resistor. So if you read a different book or a different author, sometimes as series resistor. So RS. Okay. And so if you have a fixed load, you can decide what value you want for your series resistor based on this equation. Okay. All right, let's take a pause. Let me know if you have any questions.
Professor? Uh,
Hold on, there's a
oh,
question being asked in class.
oh, no worries.
Yes. That's exactly how it works. Yes. So the point being made or the question being asked was the R load would represent the Thevenin resistance of a larger circuit. And the answer is yes, that's what it is. We simply use RL in our circuit analysis, but in real life, of course, the load could be anything. It's not a single resistor always. Yeah. Yes, go ahead. Online, someone had a question.
Yeah, in the previous configuration with piecewise linear, I just wanted to ask if IZ would be taken as negative ID and vice versa.
That is correct. Yes.
Okay, okay,
IZ would be minus ID. Yep.
got it. Thank
ID
you.
is always taken as going from anode to cathode.
Mhm.
But as I said, we just introduced it in the first example. But for Zener analysis, we typically never, we never refer to the diode current or diode voltage. We simply refer to the Zener voltage and Zener current.
Got it.
Yeah. And
Thank
we
you.
we refer to them as positive. Yeah. Okay. Any other questions before we move on? All right. So in this example, RZ was equal to 0. What if RZ had a value? As will often happen the case in real life components, right? RZ is not 0. RZ actually has a value. In this case, we have VZ as 5 volts and RZ as 100 ohms. Okay. Everything else about the circuit is the same. So if there is some Zener resistance, how does it affect our output? Okay. Analysis would follow the same steps. We have a source, and the source is applying total current IS, splits into IZ and IL, and we have VL, voltage across the load resistor. So the question here is, how is that series resistance affecting the output voltage? So output voltage, determine the output voltage and the Zener current. And of course, our assumption is that the diode is on and IZ will have some positive value or positive number. So from KCL, we can write IS is equal to IZ plus IL. Therefore, IZ, actually not IZ in this case. We want to find VL, so we simply substitute IS is 20 minus VL divided by 5,000. IZ would be VL minus VZ. Actually, let me write out the equation first. I went straight into the values. So VS minus VL divided by R, VL minus VZ over RZ, and then IL, of course, is VL over RL. Simply expressing each current in terms of the node voltages. Now I'll plug in the values. 20 minus VL over 5,000. VL minus 5 divided by 100. Note that in this case, because of the series resistance, VL is not equal to VZ. All right, rearrange the terms. You only have one unknown quantity. Solve for that quantity. You'd have our answer. So if I multiply everything with 5,000, I would obtain 50 VL minus 250 plus VL. We rearrange the terms and solve for VL. So I would get 20 plus 250, so 270 is equal to 50, 1, and 2. 50 to VL, and therefore VL is 5.1923 volts. Okay. Load voltage is not 5 because of the extra voltage drop across that Zener resistor, 100 ohms. And so instead of being 5 volts, it is now held as 5.1923. One important point to keep in mind is the Zener resistance is not a separate component, right? Zener resistance is the effect of the Zener diode. Okay, so it is part of the Zener diode. Even though our load is connected in parallel physically simply to that Zener diode, it is seeing both the Zener resistance as well as the Zener voltage. Schematically, we draw it separately as a series resistance, but it's physically part of the Zener diode, cannot be separated. So when we are designing circuits, we have to, or we must take the Zener resistance into account. Okay, questions? All right, then let's find. Yes, output voltage would change. As we see here, 5 volt Zener is providing 5.1923. Okay, so now IZ can be obtained from VL minus 5 divided by 100. IZ is 1.923 milliamps. 1.923 milliamps. And since IZ is greater than 0, our assumption that the diode is on is valid. Okay, assumption is valid. So this is what we will simulate in the lab next week. Okay, Zener diode characteristics, and then load regulation, voltage regulator. All right. Do the steps make sense? We have load line analysis, we have piecewise linear analysis, and then we have an application of voltage regulation. Okay. Load line analysis is again something we will see when we get to transistors, but the approach remains the same. We have a device characteristic given to us, and then we plot a load line on the characteristic, and we find the operating point of the device. Okay. One final point I'd like to make about Zener regulators or just voltage regulation in general. There are two kinds of regulation: load and line. Okay. Load regulation means if the load changes in value, how does my output voltage change? Okay, so there's a parameter that is used to describe, and that is known as load regulation. And then if the line voltage changes, then how does my output voltage change? And that is described by a parameter known as line regulation. And both those parameters are expressed as a ratio of voltages, or the change of output voltage VL as a function of the input voltage, or the change in the output voltage VL as a function of the load resistor, or change in the load resistor. Okay, so let me write those down right here on this side. Load regulation is basically change in output voltage. Oh, it's a function of load current, meaning if RL changes, and then line regulation is basically change in output voltage or change in source voltage. Load regulation can be given from RZ minus RZ over the series resistance R, and line regulation by the ratio of RZ and R plus RZ. Okay. There is, of course, a whole lot more theory and other factors that we can use when we design. But at its simplest application, if you put it all together, then you can design a DC power supply by taking, let's say, a transformer. Transformer steps down the power outlet voltage, let's say from a 120 volt power outlet, steps it down to 15 volts. At 15 volts can be given to, and I'm just throwing out some random numbers, the 15 volts can be given to a bridge rectifier circuit. The output of the bridge rectifier circuit will now drop to 15 minus 1.2. So about say like 13.7, 13.8 volts due to the diode voltage drop. We apply a filter capacitor in there. Let's say we have a filter capacitor of 10,000 microfarads, will result in a peak to peak ripple of 100 millivolts or less. So from 13.8 volts, we now have a flat line of, let's say, 12.5, 12.6 volts with some sort of ripple. And then we give that into a Zener diode. Let's say our output requirement is either 5 volts or 7 volts or 9 volts. But if our output voltage from the filter capacitor is above 10 volts, we can safely connect a Zener diode and obtain that value, at least safely up to 10 volts. Did all of that make sense? Let me draw it out. Let's do that. Let's do that. So if we put it all together, right, we want to create a power supply at its simplest form without worrying about a lot of other factors, we would need a transformer. You're applying 120 volts. The output of the transformer, let's say it's 15 volts, goes to a bridge rectifier circuit. Where the output of the bridge rectifier circuit would be about 13.7 or 13.8 volts. And that can be connected to a capacitor. Let's say the capacitor is 10,000 microfarads. And then we connect a Zener diode depending on our requirements. We'll also have a current limiting resistor in here somewhere. And this would be RL. VZ could range from, let's say, anywhere from 2 volts, let's say 10 volts. This is without considering any other factor, okay, to ensure that the diode would turn on. All right, questions? Yes.
So the capacitor is in parallel with the diode, right? But doesn't mean that the capacitor is not discharging, right?
No.
It's still discharging, but it's discharging into the resistor, but not the diode.
Well, that's a good question. So the question being asked is whether the capacitor discharges through the Zener diode or not. That would be part of the consideration of designing supply. So we take the Zener resistance into account, and then we'd see what happens when it discharges. Hence, we choose a very large value of the capacitor. So even if it does discharge, now the size of the capacitor is quite large compared to the Zener resistance. So even if it tries to discharge, it's going to be a very slow process. Yeah. And remember, we had the equations for the ripple voltage in the filter capacitor, right? Depending on the size of the ripple, we choose a filter capacitor. And so all of that is taken into account when you're designing a power supply. But this is the bare basics, right? If you want a quick and easy design, this is something we can come up with. Okay, quiz as usual on Monday, based on the material we have covered this week. So that would be diode rectifiers and the Zener diodes. There will be a homework forthcoming for the Zener diode. Maybe one problem, maybe a few short answer questions. So Friday, Saturday, Sunday, and then quiz on Monday. All right. Okay, we'll end class here today, and I will see you all on Monday. If you have any questions, we still have 10, 11 minutes. Again, also, I have an off-campus appointment, so no office hours today. I'm attending an online seminar workshop, so from 12 to 4. So I will be in the office, available from 4 to 5, if anyone needs to see me. Okay. All right. Do you have a question? It's still there. We figured, yes.